In lecture 4, we will be discussing local deformation rates and specifically the volumetric strain rate will be the leftover item that has not been discussed so far, so that will be taken up in this lecture. Remember, we have already covered the longitudinal, the shear, and these deformation rates. So the volumetric strain rate in a fluid particle is left to be discussed. So the learning objectives of this lecture are to obtain the instantaneous volumetric strain rate for a fluid particle in a coordinate free form. Now this is something that we is a sort of an important you can say new concept that we will introduce in this course. Most of the expressions that we will develop and we will try to pass on to you will be in a coordinate free form. Coordinate free form means that they will be expressed without the help of any specific coordinate system like Cartesian or cylindrical, polar, or whatever. We will not be encouraging ourselves to develop expressions with a specific coordinate system in mind, because that becomes a restriction. Then you can only use that expression with that choice of the coordinate system, whereas the expression should be evolved from basic physics rather than connected or attached to a specific coordinate system. So that is the idea of coordinate free forms. Even the governing equations and everything, we'll try to, as far as possible within the scope of this course, we'll try to develop everything rather in a coordinate free form, at least the basic aspects in coordinate free form. So that will also involve telling you how to use a specific coordinate system from starting from a coordinate free form. So if you have got a coordinate free form, how to use it for a specific coordinate system. Then we would like to express the volumetric strain rate in different coordinate systems, as I have told you, starting from coordinate free form, particularly the two most popular systems, Cartesian and cylindrical. Okay, so to start developing the concept of volumetric strain rate, of course, volumetric strain rate of a given fluid particle at a certain instant of time. So if you remember, as per the continuum concept, any point in the flow domain at a given instant of time will be occupied by a tiny point-like particle. So when you attach yourself to a point in the flow domain at a certain instant of time, you are basically attaching to a fluid particle at that point. So basic idea is that at a given time instant, at a certain point, if you can write the volumetric strain rate, that will be the volumetric strain rate of the particle that is residing at that point, at that instant of time. So in this case, while you had used a tiny portion or infinitesimal material lines, tiny portion of a timeline or material line, or infinitesimal material lines to develop longitudinal and shear strain rates. For a volumetric strain rate, it is necessary to consider a particle or a point. Okay, so you can't be working or you can't be talking of volumetric strain rate for infinitesimal material lines, because lines don't have a volume. Okay, so that's why we will be just considering a point in the flow domain. Now The basic approach, because since I don't want to use any kind of a coordinate system to develop these ideas, so this is a very innovative and elegant way of deriving the volumetric strain rate, what we are going to show you here. So to start with, we have a point A, as you can see in the figure, and we consider a finite region R surrounding the point. That means the enclosed curve that I have shown, a boundary sort of, so to say, at a certain instant of time, this will be the finite region surrounding the point, and of course it contains then infinite number of fluid particles. Not only my fluid particle at point A, but a whole set of fluid particles inside this region R. And I'll show you that it's possible to derive the volumetric strain rate of this material region R. Okay. So the region or the set of particles that are inside the enclosed region shown by the closed curve, you can get the volumetric strain rate of that region. And once we get the volumetric strain rate of this region at a certain instant of time, then we will invoke the limiting process of progressively reducing the size of this region till you end up with the fluid particle at point A. So the idea is that get the expression for the volumetric strain rate of this material region R, and then examine its limit as the size of this material region reduces progressively, is reduced to smaller and smaller size, ultimately for it to coincide at point A. The region will shrink to the point A, or will be imagined to shrink to this point A. So this is the essential idea. Now it only remains to do the mathematics formally, so we will start doing it. So in order to get the volumetric strain rate of this region, we just have to focus on a small point B on its surface and a tiny area that surrounds this point B. So we call that as the small area element. Okay. Now, as you know, the areas are generally treated as vector quantities with their directions specified by the unit normals. So there is a unit normal at point B, which is n cap, and the magnitude of the area is, let's say, ds, differential small surface area element. And you will appreciate that the velocity, instantaneous velocity, fluid velocity at point B would be tangential to the streamline passing through that point at B. So in general it may be totally misaligned with the unit vector n cap, so as shown in the figure. Now if you allow a small time interval to pass by, that means suppose you are observing this over a small finite time interval, then you will see that this point B would move, and not only point B would move or translate in space, the area element surrounding that point B would sweep out a certain volume in space, as shown in the figure neighboring to the material volume figure. So you can see that the area would sweep out a volume in space, and the movement of the area is over a interval of time. So we can say that the movement will be along the velocity direction, and if the time interval is delta t, and if let's say we have the average velocity of during this interval as v ensemble, then we can say that v angle brackets में velocity जो indicate की हुई है right hand side पे, that is the average velocity. So the average velocity multiplied by delta t would be the length of this swept volume region, and in general the areas at the two ends will be in general different, because as we know that when fluid moves, it doesn't necessarily mean that the areas as it moves will not change. They may change because of some sort of shear deformations going on the particles residing on these areas. So therefore, the idea is that longitudinal deformations along the area elements between particles. So in general, the area, its orientation, magnitude can be different. The idea is that we don't necessarily have to choose the same area at the two ends. So now if I were to write down the volume swept by this small surface area element, which I have written as delta V cross element at B, that should be conceptually straightforward, because you can just use the mean cross-sectional area and take the dot product with the cross-sectional area being treated as a vector, of course. So you know that any parallel pipe that you have in geometry, you have learned this in vectors, then if the cross-sectional area is written as a area vector, then area vector dot the length of the parallel pipe, the length vector of the parallel pipe, that gives you the volume of the parallel pipe. So this volume is being considered like a parallel pipe. Of course, it's not exactly a parallel pipe because the areas are changing, but if I choose to work with a mean cross-sectional area, then it can say that the volume would be mean cross-sectional area and dot product with the length vector of the parallel pipe, which is V delta t. Now this V is the average velocity during the time interval delta t. It's not the instantaneous velocity. Okay, so has to be the average velocity during the time interval delta t. Now I can continue writing formally. The mean cross-sectional area vector can be written as a1 vector plus a2 vector by 2 and dot product with the mean velocity and delta t, and the area vector 2 can be generally written as area vector 1 plus some change in the vector area vector, so a1 plus delta a, and if I use this in the above expression, I get along very nicely. A1 plus delta a by 2 dot with mean velocity delta t, and I open out so that I get two terms, a1 dot v mean velocity delta t plus delta a by 2 plus mean velocity delta t, and our original area a1 was the differential area at B that we had considered. So it is written as ds n cap, since it is treated as a vector, so ds n cap and dot mean velocity delta t plus delta a by 2 plus mean velocity dot mean velocity delta t. Right, so the change in volume of region R in a small time interval delta t, we can get this change in volume for the entire region R if I sum up or integrate these small swept volumes or changes in volume which are local to any surface point B. Okay, So delta V element, if I just have to, if I just integrate over the entire surface S of the material region, then I get the change in volume for the region R, which is written as delta V cross and subscript R. So remember, this is a change over a finite time interval. So on the basis of the expression that we had just developed for the elemental volume change, it just needs to be integrated over the surface S. Okay, so what we have is this. Now the first term is integral surface area V dot n ds delta t, and then plus we have integral delta A dot with the mean velocity V delta t. Now here this ds, which is written at the end, this is a sort of a error in my writing. Actually, this ds should not have been there. Only the volume needs to be summed up over the entire surface area. So the double integral should be there, and delta A dot ensemble V delta t by 2. So please make this change in when you read off or make notes from this lecture. Don't use ds in the second term. Anyway, that doesn't bother me, because later on I'll show you that this term in the limit delta t going to 0, this term will go to 0. So volumetric strain rate of region R is given as limit, because I need the instantaneous volumetric strain rate of region R. So what I'll do, change in volume upon original volume and divide by delta t and take the limit delta t tending to 0. This is how you define the strain rate of any type. Okay, the change in length or change in volume in the numerator divided by the time interval upon the original volume. So that gives me the volumetric instantaneous strain rate of region R. So if I look at the limit, then because I am dividing by delta t, then so I have a term which looks like this: limit delta t tending to 0, 1 by V, the original volume of the region R, and the bracketed term is surface integral of the mean velocity dot n ds plus the surface integral of delta A dot V by 2. That small ds should be dropped. As I said, that's not correct, it's incorrectly written there, ds. So surface integral simply delta A dot V by 2. And notice that as delta t goes to 0, in the limit as delta t becomes very, very small, the mean velocity should become the instantaneous velocity V, and the delta A, of course, the change when the elemental volume was visualized, delta A was the change in the area, cross-sectional area. So if delta t becomes very, very small or tending to 0, so obviously the change in area would also go to 0. We are left with, in the limit delta t tending to 0, we are left with only the one term, with the delta A term just vanishing. So all that it was doing, delta A considerations and all, they were just providing you the rigorous correctness in the derivation. Okay, they were there because you were considering finite interval of time. So the delta A terms or their effects are gone when you take delta t, limit delta t tending to 0. So the volumetric strain rate epsilon V for the region R turns out as 1 over the original volume V, and the rather original means the volume, instantaneous volume V of this region R. And if you were to integrate V dot n over the entire surface of this region, material region R, then that integral divided by the volume of the region simply gives you the instantaneous volumetric strain rate of region R. So I again repeat, for a region R, the volumetric strain rate comes out as integral of the normal component of velocity on the surface, integrate over the entire surface of the region R, and divide by the volume of the region. V dot n simply represents the normal component of the velocity, local velocity at any point on the surface of the region R. You integrate it over the entire surface, divide by the volume of the region R. That gives you the volumetric strain rate. Now, to move forward, there is an interesting application of a very popular theorem from vector calculus. So by now I hope you have downloaded my two very necessary and essential and useful sheets regarding various mathematical theorems, identities, and various rules from vector calculus that we have, which will be very useful in our fluid mechanics course. So I am talking of the second sheet, which is by the name of mathematical identities from vector calculus and mathematical theorems and things like that. So that second sheet, if you go into and look into it, you will find a very important theorem by the name of Gauss Theorem, and this is a very popular theorem from vector calculus. So what does this Gauss theorem say? It says that if you've got some kind of a vector function, in our case it is the velocity field, so it's if you consider any region, material region in the flow domain, and you integrate over its surface the normal component of the velocity field V dot n ds, then this surface integral can be readily shown to be equal to the volume integral of del dot V, or which is known as the divergence of V. Now this is a new operator. We will discuss this immediately after the deriving the volumetric strain rate at a point. So let us for the time being defer this understanding of this operator symbol delta, or the inverted triangle. We simply call it as del operator, and del dot V, this particular this operation, that when you operate the del operator, so to speak, and you operate it on a vector function, in our case the velocity field, and since this operator, let me tell you, is actually a vector operator, it's not a scalar operator, so it has to be operated on a vector either through a dot or a cross product. So when we operate it with a dot product, we call it as the divergence operation. We are taking the divergence of the vector function V. So del dot V, if I was talking of the Gauss theorem, so the surface integral of the normal component of the velocity over a surface of a material region R is equal to the integration within the region R, or the volume of the region R, of what? Of del dot V. So that means I can replace my surface integral using the Gauss theorem in terms of this volume integral. So my volumetric strain rate of the material region R can be equivalently written as 1 over the size of the region, so V cross, and integrated in the volume del dot V. So now comes the main question. We were not actually having this objective of finding the volumetric strain rate of a material region R. We had said that we would like it to be the volume strain rate of the point or of the particle at point A. If you go, if you remember the original figure that I had sketched in the previous slide. So, and I had also pointed out that this we can achieve if we can find out the volumetric strain rate of the region R, and then try to imagine that if this region R, since the size and shape was quite arbitrary, so next we pose the question that if suppose we progressively visualize smaller and smaller sized material regions surrounding this point A. Remember, I am not actually physically shrinking this region R in time. Time is rather a coordinate which is held fixed in this process. Okay, you just have to think in terms of choosing progressively smaller and smaller material regions surrounding the point A. That means start with a smaller region every time. So when we progressively start with a smaller and smaller material region, we will keep on arriving at this result that epsilon VR will be 1 by the size of the region and integrate in the volume del dot V dV. So therefore, we would like to ask the question, what is the limit of this expression that we have here, 1 by V cross volume integral del dot V dV? What is the limit if the volume that I start with initially is actually infinitesimal? That means it is actually the point itself, the point A. So in order to do this, in order to estimate the instantaneous volumetric strain rate of a fluid particle at A, we take the limit of epsilon VR as V becomes infinitesimal. So V goes to dV. So if that happens, let us see, the limit is very elegantly found. Limit V goes to dV, 1 by V, the expression whose limit is being sought. So what happens when the volume itself becomes infinitesimal? The volume integral, you will appreciate that the integral will actually be just the product of the integrand and the infinitesimal volume, because since you are no longer considering a finite volume, you are considering an infinitesimal volume, so the integral degenerates into the product of the integrand and the differential volume. So it is simply written as del dot V at point A and multiplied by dV. And of course, since you started with a differential volume, so the original volume which is there in the denominator is also written as dV cross. So what happens? The net result is simply del dot V at point A, because the differential volumes being present both in the numerator and the denominator, they simply cancel. So I again repeat that if you go into a limit of starting with a very smaller and smaller volumes, so exactly to get to the point A, you need to consider an infinitesimal volume surrounding point A. So the limit of 1 over V cross volume integral del dot V dV as V goes to dV cross. So limit V cross rather going to dV cross. So we get the integral, as I say, because the volume has itself shrunk to or has been taken to be a very infinitesimal in the sense of calculus, dV cross. So the integral is simply the product of integrand and the differential volume. So and divided by the volume that I have chosen. So the volume chosen was dV cross. So dV cross cancels and we have the result divergence V at point A. So this is in general the volumetric strain at any point in the flow domain. So it means that if I am just interested in finding at any point the volumetric strain rate of course, of a fluid particle that is at that point at a given instant of time. This is guaranteed by the concept of continuum. So I just need to take the divergence of the velocity field at that point. So up till now I haven't told you anything about the divergence operation and how what is this operator which we have written in the form of inverted triangle, which we are calling it as the del operator or the gradient operator. In vector calculus you might have learned maybe in some mathematics courses about this operator. So this is known as the, formally this is known as the gradient operator. We also in short sometimes refer to it as the del operator. Now in Cartesian you may be able to recall this del operator maybe from your fluid mechanics course in second year, that this del operator is I cap del del x plus j cap del del y and k cap del del z. So physically what this del operator actually does, it simply tries to get the measure of the space rate of change of any vector function. So if you have got a vector function, then it tries to give you a measure of how fast the function would be changing in space along all the various coordinate directions. Okay. Now this information is actually useful in getting the rate of change of any vector function in space along any specific direction. That is the use. So basically the del operator gives you an idea about how fast in space a vector function is changing. Right, so we will now discuss or rather show you how you can use this gradient operator in a Cartesian coordinate system and also a cylindrical coordinate system. Now the details and how the various operations involving this gradient operator for scalars and vectors and even tensor functions, because all that will be required in fluid mechanics. I have already pointed out that we have given a separate sort of a handout in the form of algebra and calculus of scalars, vector and tensor functions. This is available on my web page, and I'm again requesting you to please download it and use it or rather start studying it. I will be taking a detailed lecture on that. Probably my next lecture will be on using this gradient or the del operator, and in general on algebra and calculus of scalars, vector and tensor functions. So you should be ready with that mathematical handout. And of course there is another one which is in the form of theorems and identities from vector calculus. So there are two sheets, so you should download both of them from the web page. So now moving to how we do it in Cartesian system, you have to remember one thing. This gradient operator is a vector operator. So when you have to use it on vectors, it has to be used with either a dot or a cross product. Okay, you can't just use this vector operator on a vector without any dot or cross product. For scalar, it is used without any dot or cross product. It's simply used as a gradient operator. But for vectors, there has to be a dot or a cross. Even for tensors, later on we'll show that you should have a dot or a cross involved in the gradient operator. So what result we have for the volumetric strain rate, we need del dot V, right? So there's a dot product involved between the del operator or the gradient operator and the velocity vector. So we start writing the operators and the vectors using the unit vectors of the coordinate system in which we choose to work. So since I am working in Cartesian, so I'll use the ijk unit vectors. So the del operator is written, and then dot with the velocity vector. U, V, W are the components along x, y, and z directions. So now notice how we open out this operator. So we take the first term I cap del x and operate it on the velocity vector. So how we do it? We just push del over del x on the vector function. So we just write the del x of the vector function and retain the dot product as it is. So I dot I del x when operated on the vector will be I dot, and del x is operated on the vector. That is the idea. Similarly, j dot and del y operated on the vector. And similarly, k dot del z operated on the vector. So basically I am opening out the del operator, recognizing it as the sum of three operators, I del x, j del y, and k del z. So all three then are involved in dot product with the you can say the velocity vector, and therefore del x is means that I am taking the rate of change of the vector along x. So del x is then shifted to the vector ui plus vj plus wk, and the dot product is retained, and it will be applied after the partial derivatives are taken or are just simplified. So in the next step you can see this what I mean. I dot, then I am just writing down the partial derivatives, or rather simplifying it in terms of three terms. So notice that when I take the partial derivative del x of, let's say, u I cap, then I take the I cap outside the derivative. Why? Because the unit vectors I cap, j cap, k cap in Cartesian system, they don't change if you change the coordinates. That means, see, del x, what it means, how the vector changes if you change x. Del y means how the vector changes if you change y, and del z similarly how the vector changes with z at locally at a certain point. So therefore, since we know that I cap, j cap, k cap, they don't change with x or y or z, so in the calculus operation they are just taken out. Okay, they are not involved in any kind of a derivative or differentiation operation. So therefore ui cap del x becomes del u del x I cap, and del x of vj cap becomes del v del x j cap, and so on. So all the various terms are likewise simplified, you can say. So remember, what has happened here is that a stage was there where we have to consider the unit vectors, or rather their derivatives with respect to space. Okay, so that stage comes when you are using this del operator. Now you have to carefully examine in the coordinate system in which you are working whether your unit vectors would be changing with respect to certain coordinates or not. If they are not changing, then only then you are allowed to bring them out of the derivative operation. We will show this more clearly when we work with cylindrical coordinates. There you will see that some of the vectors are going to change with certain coordinates. So there this operation have to be done with greater care. So anyway, so moving on with the Cartesian side, the left hand side. So now we can take the dot products. Okay, so since we know that it's orthogonal vectors, orthogonal Cartesian coordinate system is orthogonal, means all the unit vectors I cap, j cap, k cap are mutually orthogonal to each other. So I dot I would become 1 and I dot j, I dot k will be 0. So all these things if we use, we are simply left with three terms. One term from each square bracket is basically what you will get. So from the first square bracketed term, you'll only get del u del x. From second, you'll only get del v del y. And from the third one, you only get del w del z. So though we had started with a very rather sort of long and complex looking operation, but it has eventually simplified into a very small neat expression, del u del x plus del v del y plus del w del z. So now by now a bell should ring in your mind that I know the physical meaning of these derivatives, right? I have already talked about them in my previous lectures. Del u del x plus del v del y plus del w del. What are these? Del u del x is simply epsilon xx, the longitudinal strain in an infinitesimal material line along x direction with the line itself aligned along the x direction. Similarly, del v del y, epsilon yy, and del w del z, epsilon zz. So basically what we are doing to find the volumetric strain rate in Cartesian coordinate system at a point, you just have to add up the three longitudinal strains, epsilon xx, epsilon yy, epsilon zz. So sum of three longitudinal strain rates actually gives you the volumetric strain rate. So you can see that although the derivation was very general, it didn't require any volumetric strain rate derivation, didn't require any coordinate system in mind. So it can be accepted as a very general expression, del dot v, apply, and it can be used freely for any kind of a coordinate system. We have already seen that how the result looks like in a Cartesian coordinate system. Now let us move on to a cylindrical coordinate system. So a brief introduction of how the coordinate system looks like. So basically you have a horizontal plane which I have shown with the help of two lines, and from one of the lines which I call as the reference line, you consider the angular coordinate theta, and so this angular coordinate theta helps to locate the plane in which the vector OP lies. P is any point in space which is going to be described by the cylindrical coordinate system. So this point P has a position vector OP from a chosen origin O. Now this OP vector can be made to lie in a plane as shown, and that plane will in general have some kind of angle with respect to your reference line theta, which is shown, and then the unit vectors are also shown. All three unit vectors are mutually perpendicular. So the radial vector is along the r coordinate, which is basically the length of the projection of OP in the horizontal plane, which is OQ, and E theta is the unit vector, which is the theta direction unit vector, which is normal to ER and in a direction of the angular coordinate theta. So since theta is being considered in the sense shown in the figure, that means if you look from the top, then it is the anti-clockwise coordinate from the reference line. So in that direction E theta is there, which is for this point Q. I am showing these unit vectors for this point Q. ER goes in the direction shown, E theta again perpendicular to that, and EZ will be the perpendicular to the plane containing the line OQ or the point Q. So this is the third coordinate direction of the cylindrical coordinate system. Now these three unit vectors are there, and so you can write the position vector OP as a sum of the vector OQ and let's say QP. So OQ vector will be written as the length times the unit vector in that direction. So R is the coordinate of the radial coordinate of point P. So it will be the projected length of the OP vector in the horizontal plane, and then if you add this QP vector, which is nothing but ZEZ vector. So the position vector OP becomes RER plus ZEZ. Now you will appreciate that any point P in the space will be having a position vector of this type only, RER plus ZEZ. You can just see that there is no theta component in the position vector. Okay, this is something very interesting. In cylindrical coordinates, when you write the position vector, it can be completely expressed in terms of a radial vector and axial vector, which we call as the z direction. So any vector in space like OP is a general vector will be a sum of the radial vector OQ and the axial vector QP. Now although the plane changes when we change theta, but the plane keeps on containing the position vector OP. So that's why the position vector itself does not contain any theta component. Now the main point that I am trying to make here is that this is a coordinate system in which if you change theta, so if you rotate the plane about the vertical axis, then you will notice that the unit vectors r and theta, they also rotate with the plane, because as you rotate the plane, the radial direction or OQ as so to speak, it changes. Okay, and the radial vector must be directed along OQ. So increase in theta, you will end up with the changes in the unit vectors ER and E theta. They will be actually from the top. If you increase theta, then ER and E theta will also change their orientations. Okay, because of change in OQ. So in cylindrical coordinate systems, we can safely say that unit vectors ER and E theta change with theta. What about EZ? Does it change with theta? No, because if you rotate the plane, the axial unit vector still keeps pointing in normal to the horizontal plane or the plane containing OQ. So there's no change in EZ with changes in theta or rotation of the plane. So rotation of the plane only changes ER and E theta. So this is sufficient for us. We need to remember this. In cylindrical coordinates, only two unit vectors change, and they only change with theta. This is what all you have to remember. They don't change with R or Z. Okay. So this can be used, and we can show that. I'm not giving you formally the proof of these derivatives. You just have to use them. And these are given in my mathematical identity theorem and various results from vector calculus sheet. These results are also given there. So the partial derivative of ER with theta, since ER only changes with theta, so it is same as the ordinary derivative, and this derivative we can show ER unit vector derivative is a unit vector E theta. Okay, so and similarly the derivative of E theta with theta is minus ER. So all this can be shown. I am not involving the proof here, but if there's a popular demand of showing the proof by the students, I can also provide the proof of this. But the proof of this is already probably, I remember, when I used to teach first year mechanics, I used to give all these details there. So I don't know whether in your first year mechanics course you learned these derivatives or not. But anyway, the derivation is not important. You see, for us the mathematical results, we need to just borrow them from the mathematicians and use them to our advantage. Okay, let us leave this exercise to the mathematicians deriving these results and all. Anyway, so remember to use these derivatives, ER and E theta derivatives, with respect to theta, and the values are DER d theta is equal to E theta, and d theta is minus ER cap. So now if you were to use these del dot V in cylindrical coordinates, you can again start by writing the del operator and the velocity vector using the coordinate system that you are considering. So the del operator in cylindrical coordinates is, notice how the terms are written. ER del del R plus E theta by R del theta plus EZ del Z. So you have to remember this del operator, how it is written in cylindrical coordinates. ER del R plus E theta by R del theta plus EZ del Z. Now, in my sheet on algebra and calculus of scalars, vectors and tensors, I have also gone into details of how we write this del operator, and also when I'll take a class on that, you will be able to understand how we are writing these in Cartesian and cylindrical coordinate systems. Anyway, for the time being, just take it for granted that del is written like this in cylindrical coordinates. Now, if you go by the same way what was demonstrated for cylindrical coordinates, and when you are involving the partial derivative with respect to theta of the various vector components, then please be careful enough to do the differentiation using the product rule, because both the component as well as the unit vector, they will change in general with respect to theta. So when you open out these things, you are requested to do it yourself, so that you make sure that you have understood the process of using the del operator and getting the divergence of the velocity field, so that you get the volumetric strain rate. So I'm just giving you the final answer that you'll get after applying the del operator on the velocity vector. Follow the same steps as we have done for the Cartesian, with the only care that when del theta is operated on the unit vector components VR, ER, on the velocity components rather, VR, ER and V theta, E theta, you have to apply the derivative using the product rule, because both VR, V theta, ER, E theta, both quantities involved in the derivative VR, ER or V theta, E theta will change with theta. Okay, and then later on, once you have got the derivatives as was shown for the Cartesian case, then last step is to apply the dot products of the unit vectors. And of course, in this case also the unit vectors are orthogonal. So ER dot ER will be 1, and ER dot E theta and ER dot EZ, they will all be 0. So you have to use that. So final result is del VR del R plus VR by R plus 1 by R del V theta del theta plus del VZ del Z. So this is the volumetric strain rate in cylindrical coordinates. So please make sure that you derive it in your notebooks, and if you need any help, then we are available. Then I can also combine the first two terms using again simple calculus concepts. So I can write it as 1 over R del R of the product R into VR, because when I open it out by product rule, I will have one term as del VR del R and the other term will be VR over R. So that's why I can combine the first two terms into a single term. Sometimes this is useful in analysis, to have a single term rather than the two terms separately. So we come to the end of this lecture 4. It was we are increasing in the order of complexity, you can say, as far as the mathematics is concerned, as we are moving on in this course. So, but we'll try to make your life as simple and straightforward as possible. We can't help it. The subject is definitely more involved in terms of physics and mathematics, so that we can't do anything about it, but we can make our life easy if we use the concepts correctly, and that's why we have provided you the additional help in mathematics in the form of those two handouts and sheets. So thank you very much for this lecture.